Good evening, everyone. I'd like to welcome all of you to our conversation tonight. And I hope that you're looking forward to this, yet another insightful evening with NYU Abu Dhabi Institute. And I know that we are getting all of you away from your digital norms into a different norm tonight to speak about beauty and physics. And I hope that you will be excited as the rest of the team to welcome Sabine Hossenfelder, who will speak with us on how beauty leads physics astray. So tonight we'll be talking about the ability to develop fundamentally new laws of nature. Theoretical physicists often rely on arguments from beauty. Simplicity and naturalness in particular have been strongly influential guides in the foundation of physics ever since the development of the standard model of particle physics. This talk would demonstrate that argument from beauty that have led the field into a dead end and considers what can be done about it. So I would like to welcome first with us here tonight, Sabine Hossenfelder, who is a research fellow from Frankfurt Institute for Advanced Studies. Sabine is a researcher and she's specializing in theoretical physics and quantum gravity. She worked and is still working as a researcher at the Frankfurt Institute of Advanced Studies, where she is in charge of a research group dedicated to gravity analysis. She dedicated herself to obtaining a master and doctorate at the Johann Wolfgang Goethe University in Frankfurt. After that, she as well obtained her PhD in physics with a thesis entitled Black Holes and Large Extra Dimensions. And I'm sure we'll get a lot of questions from our audience about this. Dr. Sabine Hossenfelder received a research fellowship from the University of Arizona in Tucson. In 2009, she was appointed as an assistant professor of theoretical physics at the Institute of Advanced Study at the University of Frankfurt. And in 2018, she also has been a researcher at the Institute in charge of gravity analysis group. Sabine with us today because she acquired a special notoriety, and I'm sure you follow her tweets online because I'm a follower of your tweets online as a science communicator. Among her achievements is the book that was published in 2018 and entitled Lost in Math: How Beauty Leads Physics Astray. I hope that everyone in the audience will get a copy to just get into this kind of connection between beauty and physics. Sabine, the floor is yours, and welcome on the Institute platform.
Thank you so much for the introduction. I'll try to share my screen, and please bear with me. Does this work?
Perfectly.
Okay, great. Okay, wonderful. So as you just heard, I've been working in the foundations of physics for like about 20 years almost. And I want to start my presentation today by explaining why I'm here, why I'm talking to you, why I'm giving public lectures. In the past couple of years, I've become very outspokenly critical of what's going on in the foundations of physics. And I'm giving public lectures. I've written a book, I have a YouTube channel, I've written contributions for quite a few popular science magazines. And I want to put ahead today that the reason I'm doing this is not that I think there's something wrong with research in the foundations of physics. On the very contrary, I think it's super important, and we have to push more on it. It's just that I think that the way it's being done right now, we're not making any progress, and we have to work on this. And so before I tell you anything specifically, I have to make clear what I mean by the foundations of physics. Foundations of physics I refer to are those areas in physics where we are concerned with the natural laws that cannot be derived from any underlying laws. And that's currently the behavior of space and time, which is described by Einstein's theory of general relativity, and then the smallest constituents of matter and how they interact, which is described by the standard model of particle physics. Those are only some parts of physics. There are lots of other areas which are not the foundations of physics, like optics, quantum optics, big parts of astrophysics, condensed matter physics, material science, all that kind of stuff. So those are, at least in my vocabulary, not the foundations of physics. So in the end, that's just a terminology, but that's how I use the word. There are always some physicists who are a little bit offended that I don't count them to the foundations of physics, but if they hear my criticism, they usually relieve that they are not in that group. So what's going on in those areas of physics? Well, there's a lot of talk about crisis. This isn't new. This has been going on for a long time. Crisis at the edge of physics. So that's the foundations of physics. Foundations of physics, it's got something to do with supersymmetry. Could there be a crisis in physics? Another crisis in physics. Is theoretical physics in crisis? Yeah, so we will die before we have the answer. So this all sounds very not good. What are those people talking about? I should probably put ahead that if you talk to my colleagues in the foundations of physics, a lot of them would disagree that we have a crisis. Because they see a lot of progress around them. You know, it's not that people aren't doing anything. They're certainly writing papers, there are conferences, everything is very, very exciting. But if you look at what comes out in the end, it's not a terrible lot. And I think everyone who has looked at this objectively, like from the outside, would agree that there has been pretty much no progress for a long time. So we've seen this stagnation pretty much since the mid-1970s. So we have general relativity on the one side, as I said, on the foundations of physics, but that theory is more than 100 years old. And on the particle physics side, we have the standard model, which was, for what the mathematical formulation is concerned, completed in the mid-1970s. And so what's happened after this is certainly that we have experimentally confirmed some of those particles in the standard model. Like in the 1970s, there were some of the heavier quarks had not yet been measured. We have also later figured out that neutrinos have masses, so there's a particular type of particle that have masses, but the theory for this goes back to the 1950s. And the most recent experimental discovery has been the Higgs boson, which you probably remember made big headlines in 2012. And this was kind of the last missing particle in the standard model. In general relativity, we've confirmed the direct detection of gravitational waves, so they have been indirectly confirmed several decades ago already. And we've also put the cosmological constant back in, and there has been a Nobel Prize for this, but the cosmological constant was also already introduced by Einstein. So it's not like there's something new. So the mathematical formulation of those theories has remained entirely unchanged. And now you could say, well, maybe that's just it. You know, we've done it. Those are the foundations of physics, and that's the end of the story. We can all go home in that area. But no, we know that that's not it. Because the standard model doesn't fit with general relativity. We're missing a theory of quantum gravity. This is, in my mind, like the biggest shortcoming that we have in the foundations of physics right now. We know that nature somehow knows how to do it. We have all those particles in the standard model, and those particles have masses. And we know if you have a whole lot of them, they have a gravitational pull, and we can measure this, but we don't actually know how those quantum particles get their gravitational pull, because general relativity is not a quantum theory. Those two sides just don't talk to each other. And this has been a long-standing problem. It's been known since the 1930s, but we have made pretty much no progress. And there are other problems in the foundations. For example, you've probably heard that astrophysicists say that about 85% of all matter in the universe is a peculiar type that's called dark matter, which is not in the standard model. So it's a little bit controversial. It could also be that instead we don't really understand how gravity works. This is called modified gravity. So those are kind of the two competing hypotheses. But what's certainly clear is that if we look out into the cosmos, like not in our solar system, but on the scale of galaxies or galaxy clusters or even galactic filaments, back in the early universe, cosmic microwave background, that kind of thing, then we just can't explain those observations if we just take the standard model and general relativity. It doesn't work. So either way, whether there's a new type of matter or if we have to change something about gravity, the foundations can't be right exactly the way that we have them right now. And of course, there are lots of other questions like the measurement problem, quantum mechanics, how did the universe begin, and so on and so forth. I'm sure those are questions that you have talks about on other occasions, so I don't want to go through the whole list. I just want to give you a sense that there are open questions, so we're definitely not done. And now you can say, well, why should we be worried that progress has been slowing down? Those are hard questions, and maybe it's just really, really difficult to find an answer. So why worry? And I would agree. Physics is a very mature discipline. It's one of the first disciplines of science that has ever appeared in the literature, and the simple things have just been done. So to some extent, a slowdown is unsurprising. But we also have to take into account that the number of physicists has been growing exponentially in the past 100 years or so. So there are also many more people working on it, which brings together much more, total work time on those big questions. Also, as I said, it's not that people aren't doing anything. They're hugely productive if you look at the amount of papers that they write. It's just that all that work doesn't really lead to anything. And that brings up the question, like, why not? Why do they produce so many papers that are so completely useless? And I think the reason for this is that ultimately the problem is not that those questions are difficult, though they are, but those are also really, really smart people. The reason is bad methodology and groupthink, and I'll explain in more detail while I say that. I've been told I shouldn't call it groupthink, that's kind of impolite and just makes people aggressive. The technical term is social reinforcement, but the problem is if I say social reinforcement, then no one knows what I'm talking about, so I'll keep calling it groupthink. The problem is, as the title of my talk already indicated, physicists rely on arguments from beauty, and they come in with different names. Naturalness is one of them. There's unification, there's simplicity, and so on and so forth. And I've written an entire book in which I go through those different types of beauty and exactly how they enter the foundations of physics. But in this talk, I just want to give you a general overview on what's gone wrong. So the issue is that physicists think that the foundations of physics are not pretty enough. And then they invent theories that are prettier according to certain mathematical notions of beauty. And then they make predictions from those theories and are surprised if no evidence is found that supports their theories. And an added problem is that they are largely unaware that this is what they are doing, because those requirements of beauty have become mathematical standards. It's not like they write a paper and they start with saying, now I assume that this theory has to be really, really pretty. No, that's not the way that it works. They make an assumption like, we assume that the theory has to be technically natural, and then they write down an equation, and then they just assume that this equation has to be fulfilled. But they never stop and ask, why should we require this? Like, why does nature have to fulfill this criterion? And this has led to a lot of failed predictions. And you've probably noticed this yourself. Like, if you read headlines about the foundations of physics, they'll normally, if there's any experimental result, it'll just tell you they haven't found the thing. Like, they haven't found this dark matter particle, they haven't found this fifth force. There's still no evidence for quantum gravity. We still haven't found any evidence for parallel universes and so on and so forth. Maybe not so surprising. And if you read something about the ideas that they have, it'll always be something like, physicists think there may be, I don't know, a new force. There may be another particle, and maybe we can see something with that kind of experiment. My impulse is always to say, well, yeah, maybe, but maybe not. And then you never hear anything about it again. So I'm afraid that it's fairly easy if you only read those headlines, you become very cynical about what people even get paid for if they work in the foundations. And so here are some of those failed predictions that were based on arguments of beauty. One of them is a particle called the axion. So the standard model, it contains 25 particles, and there are lots of different parameters in the standard model, one of which is called the theta parameter. And the theta parameter is very small. It's actually so small that we're not sure if it's maybe not zero. And now the thing is that physicists don't like small numbers. If there is a small number, there has to be an explanation for it, and that theta parameter doesn't have an explanation. So they just think it's ugly. If you just assume it has a very small value, that describes all our observations perfectly fine, but they don't like it. So what they do is they make the theory more complicated, and that explains why this theta parameter is small, but it has the side effect that it also predicts a new particle, which is called the axion. So this is not a new story. This was done already in the 1970s, and people looked for this axion particle, and it was ruled out pretty much as quickly as was predicted. It's just grossly in conflict with astrophysical observations. But what happened next is not that physicists, gave up on this hypothesis. Instead, they amended it so that it would still be compatible with observations. And that's very symptomatic for what would follow many times over and over again. So they called this modified axion the invisible axion. And there are still experiments looking for it. You see an image of such an experiment in the corner. But none of those experiments have found the axions. The problem is they're invisible. They were created, the entire theory was made so that they would be difficult to measure. Also, it's not surprising that they turn out to be difficult to measure. There's another type of those failed predictors is quite related to this. The standard model is not as symmetric as it could be. So you see on the right side, you see a sketch of all the particles in the standard model, and it looks kind of not particularly appealing. It looks a little bit random. Actually, I drew this image for my book. And I was quite unhappy with it because I thought, it doesn't look nice. And I looked online what other illustrations people have made, and you can do this yourself. Just Google the standard model of particle physics, and you'd find a lot of illustrations where they use a very nicely symmetric round design. And I thought this would be much nicer. So I tried it, and then I realized it doesn't really make physical sense, the way that these particles are paired to each other. And then I realized, I'm doing exactly what I'm telling people they shouldn't do. They shouldn't try to make the laws of nature prettier than they actually are. That's just the way the standard model is. And it isn't pretty to our eyes, but that's just the way that it is. And so I stuck with this kind of random looking picture with those different groups of particles. But so now what a lot of theoretical physicists have done, they were so unhappy with this collection of particles that they try to combine them in one big symmetry group. And that's called a ground unified theory. And those theories, there are different ones of them, but they generically predict that protons are unstable. So protons are one of the constituents of the atomic nuclei. And the good thing about this is that protons are really, really cheap. They're everywhere around us. And it's not difficult to put a large number of them together, for example, in a tank of water, and just observe it very, very closely to figure out if one of those decays, and so far no one's seen a single proton decay, and that has actually ruled out some of those ground unified theories. But the same thing happened again as with the axion. Physicists have fumbled around with those theories and made them more difficult, and so there are still some of those versions that haven't been ruled out. It's a similar story for all kinds of extensions of the standard model. So besides this theta parameter, there's a second parameter in the standard model, which is smaller than physicists would like it to be. That's the mass of the Higgs boson. This is also considered to be ugly. And physicists have put forward a huge number of ways to make it prettier. The best known one may be supersymmetric particles that are supposed to cure this problem, but there have been other ideas like extra dimensions, gravitons. Those have the side effects that you can have black holes. This is the topic that I wrote my PhD thesis on, as you heard earlier, and there were loads of other ideas. And those were all predicted on the grounds that the mass of that there's allegedly something wrong with the mass of the Higgs boson. And all those things should have showed up at the LHC basically in the same energy range as the Higgs boson, and that just didn't happen. So again, this prediction turned out to be wrong. It's a similar story with a type of particle that's called weakly interacting massive particles, and those can be supersymmetric particles, but doesn't have to be. They could also be different ones. Again, this is not a new idea. They have been looked for since the 1980s, and every time an experiment comes back empty-handed, so they haven't found the particle, then the theoreticians say, well, it's just a little bit more weakly interacting, you have to build a bigger detector. And what you see in the corner, this image is the Xenon 1P dark matter detector. That's an upgrade from the Xenon 100, which is an upgrade from the Xenon 10, which is an upgrade from the original Xenon detector. And I just read the other day that there will actually be an upgrade after the Xenon 1T. So this, theoretically, this could be an infinite story. You can always say, well, it's a little bit more weakly interacting. And why did they think that this particle should exist? Because there's a particular numerical coincidence which makes it particularly appealing. And the original version of this numerical coincidence has long been ruled out, but they just can't give up on this idea. And then in cosmology, we have allegedly a problem with the cosmological constant. The cosmological constant is also just a constant of nature, but it's very small. And again, physicists don't like this. So they have come up with all kinds of difficult explanations for why it's small. Those are particular type of fifth force or dark energy fields. And again, they've made lots of predictions for how those should show up, but not a single one of them has any evidence to back them up. So I think this gives you an idea. They've put forward a lot of theories that have just been ruled out, and in my mind, the reason is that they rely on those arguments from beauty to even develop those theories. So you may ask, like, why should we even believe in those predictions? So why do physicists believe in this? This has given me a lot of headache. And I think the reason is, in a nutshell, because they don't think about what they're doing. When you ask them, a lot of them will claim that, well, it worked for Dirac and Einstein because Dirac and Einstein, they were both talking about the beauty of their theories. And that's right, but that doesn't. So for one thing, they both started talking about the beauty of their theories after they knew that the theories were successful. So that's rather symptomatic. Actually, you still see physicists doing this today. After they've won a Nobel Prize, they become convinced that it was their sense of beauty that led them there. But that's somewhat questionable. But even if this was right, it would be cherry-picked data. You have to look at all those people who used arguments from beauty and it didn't work. And so we can have a look at some of those ideas. There are plenty of them in the foundations of physics where people have used arguments from beauty and it didn't work. The best known one may be the Platonic sonnets, which you see in this Wikipedia image. So this was an idea by Kepler that you could stack these polyhedra inside of each other, and the ratio between the radius of the spheres would tell you the ratio between the orbits of the then known 5 planets, because there are only 5 of those regular polyhedra. So this is obviously wrong, I mean, for various reasons. I mean, to begin with, the orbits of the planets are not circular, and also there are more than 5 planets, and so on and so forth. But also the circular orbits by themselves were considered to be beautiful, but in the end turned out to be wrong. There was a peculiar period in the foundations of physics where quite a large group of physicists became convinced that atoms are actually knots in an invisible ether, and you see an example of a knot there, so what mathematicians call a knot. You know, there's a certain beauty in this, but this too turned out to be wrong. And there's the steady state universe that basically says the universe has always been this way and will always continue to be this way. And we know today that this is just wrong. There are a lot of physicists, for example, Werner Heisenberg, Einstein, Eddington, and so on, in their late years, tried to develop unified theories, and all of those turned out to be wrong. And on the other hand, we have ugly ideas that work just fine. For example, quantum mechanics. So personally, I don't think it's ugly, but a lot of people think it's ugly. In quantum field theory, we have a method that's called regularization that Dirac, for example, thought just means that quantum electrodynamics, which is one of the quantum field theories, has to be wrong because it relies on this procedure, but it turns out to be correct, and we still use it. Those elliptical orbits, I already mentioned this, and the Big Bang, you know, the contrast to the steady state model of the universe, that was originally considered to be ugly. So basically the short summary is there's no correlation between beauty and explanatory power. So some ideas that work are ugly, and other ideas that are beautiful but don't work. There's also no reason to expect that our sense of beauty would give us an edge in developing the fundamental laws of nature. Evolution just didn't prepare us to look for laws that dictate the behavior of things that we can't even see. Also, this is a point which has been made by the philosopher James McAllister. Standards of beauty change, and this is another reason why you shouldn't start with them. It's just it's a cultural thing. It also has a lot to do with our education and so on. And this means that constructing theories by demanding specific types of beauty puts the carriage before the horse. The ideals of beauty change in scientific revolutions, and McAllister goes through several examples on this. And in my mind, it's just doing things the wrong way around. It's describing nature. It's the success in describing nature that makes a theory beautiful. We shouldn't start with postulating a certain type of beauty and then expect it to describe nature. That evidently just doesn't work. And I think this is why we're in this phase of stagnation in the foundations of physics, because we ran into a vicious cycle of lacking data because of those sloppy predictions. It's certainly true, as I said at the beginning, that physics is a very mature discipline. And one of the consequences of this is that it takes increasingly more time and money to test new theories. You know, we're shooting satellites into orbits, or we're building big particle colliders that have tens of kilometers of circumference, and those things cost tens of billions of dollars and then take decades to build. Or think of the gravitational wave interferometer, that kind of thing. That it takes a really long time, and you don't tinker around with experiments of that size. And this means we have to choose really, really carefully which theories to put to test in the first place. If we make a wrong choice, we get negative experimental results, which basically means we don't find anything. Now, negative experimental results are also results, all right. But if you want to develop a new theory, they're not particularly useful results. What you want is, you want evidence of new phenomena for which you can create your theory so that it describes them properly. If you only get negative experimental results, you aren't any wiser, and you're still stuck with the same data you had previously. And so physicists have just gone on this way. You know, they don't get any new data. They put forward another unpromising theory, and that gets tested, and back comes another negative result, and so this vicious cycle continues. And I think that's why we haven't seen any progress on the foundations of physics for 40, 50 years. So my progress proposal would be that we look at what has historically worked. So there have certainly been breakthroughs in the foundations of physics that were driven by coincidental discoveries. And so this is just something that we cannot rely on at this point, because as I said, it's really difficult to make a new experiments. You're not going to find a new theory of nature just by tinkering around with toys on your desk. It's just not going to happen. We have to be really, really careful about what kind of experiment we do. So the role of theoretical physicists has dramatically changed, because we have to be really, really careful what kind of theory to even test. And I think theoretical physicists should focus on resolving real inconsistencies in the theories. So they shouldn't try to make a theory prettier, because that didn't lead anywhere, and it also doesn't really make sense. Instead, they should try to solve real mathematical problems, and lack of beauty just isn't a problem. So now you may wonder, well, what are those real problems that I already mentioned in the beginning? And this is not a complete list, of course. Those are just my favorite problems, basically. There's the slacking theory of quantum gravity, so that's really an inconsistency between those two sides in the foundations of physics. There is the measurement problem in quantum mechanics that has been known for more than a century, but physicists have just completely ignored it, and that's also what I'm working on myself at this time. There's dark matter. I already said this. This is not an internal inconsistency in the theory. It's actually an inconsistency between the theory and the observations. And there are certain aspects of dark matter that I would also count as an inconsistency, but it's not the order of magnitude of the cosmological constant. Okay, so this brings me to my summary. Using criteria of beauty to assess theories and to develop new theories is just bad scientific methodology. It's not only that it doesn't make any sense, we can also see, if you look at the recent history in physics, that it doesn't work. And I think physicists should stop doing it. Thank you for your attention.
Thank you so much. Thank you, Sabine, for this great conversation. I'm sure our audience is very intrigued to hear more of you and more about the topic. I would like to encourage everyone to submit their questions in the Q&A. We have a few questions that are pending, some of them philosophical and some of them because I think you motivated them to go through the philosophical aspect of the conversation. Some of them are technical. So the first question is from Reem Al-Habtari. And she's asking you, do you believe that the beauty of physics is fueled from the need to prove the intelligence of the creator of the theory, or the lack of belief of simplicity? Because you talked about there is a lack of support of simplicity when you develop a theorem of physics. And Reem is asking if it's fueled by the necessity to prove intelligence, this kind of egoistic approach, or just the lack of belief in simplicity.
That's a very good question. So I haven't thought about this before. So I would actually say, let me answer the second part of the question first, because that's easier. I think physicists very strongly believe in simplicity. So it's not that they believe in a lack of simplicity. I would actually say that they overemphasize the simplicity. For example, if you look at the theory like string theory, which has no experimental evidence to back it up. Why do theoretical physicists believe in it? Well, they believe in it because it's really simple. It starts from this one overarching idea. Everything is made of strings and the rest is details, basically. And now if you look at the mathematics, it becomes very difficult. And that's where people can prove they are intelligent, because they're difficult equations to solve. But it starts from this idea that everything is simple. Now, when it comes to intelligence, that's a difficult question, because I would say, like, personally, there are many different types of intelligence. And one thing which you see very strongly pronounced in theoretical physics is technical mathematical intelligence. You get people who are really, really good at doing calculations, and there's also a lot of crossover in the direction of mathematics in both ways, actually. Certainly, in string theory, that's very pronounced, and there isn't a priori anything wrong with that. But if you ask, for the kind of, I would say, pragmatic intelligence, does it actually describe something that we observe? Is it useful for anything? Then I don't think that pursuing these notions of beauty is a signal for that kind of intelligence, because people are completely ignoring this question, basically.
Amazing, great insight on there. And I would like to take Charles Newman question next. And Charles is asking, and possibly this is also a gateway for us, Sabine, to understand if the ecosystem around us is actually pushing us to overcomplicate the way we process physics rather than simplify it. He's saying that have Nobel Prize choices in the recent decades been positive or negative from your point of view in supporting simplistic models?
So, I think I'm a little bit of an outsider when it comes to the discussion around the Nobel Prize, because I'm generally, I generally like the choices. I don't see the Nobel Prize as so much as a statement about what's the best physics or something, but it's more like a public statement. It also has certainly political flavor to it, which you can see very clearly in the recent choice for the Nobel Prize, which went to complexity climate physics, that kind of stuff. And one also has to keep in mind that the things that get Nobel Prizes are only the ones that have been confirmed already. So, it's things like the observations for dark matter. So we may not know what dark matter is or if it's modified gravity, but we do have those observations. There's been a Nobel Prize for the cosmological constant. There are lots of Nobel Prizes for quantum stuff that I keep mixing up. And so on and so forth. So and for the completion of the Standard Model and so on, they have also in the Higgs boson gravitational waves and so on. So there have been Nobel Prizes for this. So I'm actually not sure now how this even connects to what I've been talking about, because the things that I'm concerned with are exactly the things for which the Nobel Prizes are missing, so to say, for quantum gravity. Like there hasn't been a Nobel Prize for quantum gravity. Why not? Well, because we haven't been able to make the good predictions that could actually be tested.
So I think what follows here, Sabine, is like, don't we also need to change the ecosystem? Why do we rely on this kind of one formal platform of recognition for all of the scientists around the world? Why don't you have a diverse also recognition platforms so we could push and motivate for this kind of diverse line of thought of thinking of simplistic or physics that are built around simplicity as well? Okay, so we have Arbi Ted Siraki. He's saying, thank you so much, Sabine, and your book is on my to-read list. In the meantime, he's having a question. What are the antecedents and inspirations behind your ideas? Any connections to Thomas Kuhn, for example, for instance? What inspires you to go?
So you mean about the argument in the book, or like the stuff that I do my own research on? I'm kind of not clear.
Maybe let's go through the different parts. That maybe I think he means the book in general.
Okay, well, so I mean, I've certainly read a lot about the philosophy of science and also sociology of science, and so honestly, I always feel like the philosophy of science makes more sense if you look at it from the sociological perspective. So I think it's somewhat of a mistake to treat these two things as separate, but then this is my opinion as someone who actually works in science. So I find it very difficult to tear these things apart. So I'm a little bit unhappy with what's going on in the philosophy of science, and what the way that people like Kuhn and Lakatos and so on have been going about things, because it's not something that we can pragmatically put to use, at least not most of us. So physicists, for the most part, just ignore all this talk. Like, what's the use of talking about paradigm changes or, degenerative research programs? If in your day-to-day work, that's not something that you can integrate somehow. And so I think with my book, I've tried to explain to people in my own area, but also to other people, that we have to add a little bit more self-reflection. We have to think about where are we, where do we want to go? Are our methods actually getting us there? Because all this talk about scientific methodology is well and fine, but the scientific method is not set in stone. It has to adapt as we learn new things. We learn new mathematical techniques. We learned that some things that we did previously were wrong or they didn't work. And I think that physicists have to be a little bit more open-minded there. And so I hope this explains how I fit into this corner between sociology, philosophy, and research.
It's a
beautiful... So you want me to say about my own research, or?
Yeah, please. Go ahead.
Yeah. So I'm mostly trying to listen to myself. If I tell people it would be good if we focused on solving problems of inconsistency in the foundations. I'm trying to do this myself, which shouldn't be too surprising, because the reason I was writing this book was to find out what I should spend my own time on. I started working on theories that used exactly those ideals of beauty that I've been criticizing. And I was trying to figure out, well, how can I do it better? What would be a better way to go about it? And so you probably won't be surprised to hear that the things that I've myself been working on are the quantization of gravity, though I'm not doing this at the moment, but this is something that I've been doing for a long time, and especially how to experimentally test it. And I'm now mostly working on dark matter and on the quantum measurement problem.
Amazing. So you're basically defending or reviving the research aspects that connects to simplicity and beauty of physics. Amazing.
Well, I'm trying to.
I love this. It's like a physics preservation project from a different perspective. So we have another question as well from Muhammad Haj Youssef, and he's asking, what do you think about monadology, since the monad being metaphysical would be the simplest structure from which the complex physical structure could be composed?
Yeah, so I suppose this refers to Leibniz's idea. I've always found it personally very appealing. So you have this unity basically of nature. I mean, it's a very simple idea in a sense, but I'm also very much a maths person. I need to see equations, something that I can work with, something that I can make a prediction with. And I've never managed to combine this appealing but vague idea with the concrete side of mathematics.
Got it. Very clear. So Vladimir Milosevic, he's asking, wouldn't conjecture of Maxwell's equation qualify as driven by search for beautiful, elegant, symmetrical laws? I would agree based on such example that it worked in the past.
Well, as I said, sometimes it works, sometimes it doesn't work. It's not a good argument to only look at the cases where it did work. But I would also the development of Maxwell's equations, that's a really long story, and there were lots of things that played together. But a lot of it was just driven by experiment. They observed all these things, electrical charges, electric field, magnetic fields, and so on, and Faraday and Maxwell. Faraday was a very graphic thinker. He was drawing lines and that kind of stuff, and Maxwell was the person to put it into equations. And yes, then those equations wouldn't really fit together, and he had to introduce this additional term, which eventually led to the prediction of gravitational radiation. So that's a great story. I'm not sure that Maxwell was driven a lot by beauty. At least I'm not aware that he would have brought this up. To some extent, I think if I remember, Maxwell, this is actually an example in the book from McAllister that I mentioned. McAllister lived in a time where mechanism was still quite popular. So people had this idea that everything ultimately is like little gears and things interlocking into each other. And he had this very complicated idea how those field lines would come about by some interlocking gear system, and I've forgotten the details. And it took people quite some while to accept electric and magnetic fields as primary, to just say, but that's just the way that it is. There's no further underlying mechanical explanation. So that was actually considered to be ugly. They were looking for something prettier, something that you could turn a knob on or something like this. So McAllister's books is really, really useful for shedding light on the question, just how Maxwell thought about beauty.
So we always have to understand origins from your perspective, and I love that kind of social aspect to understand it. So Kumal Tariq, he's asking, or she's asking, a lot of things in nature have order and are generally beautiful. The golden ratios is one example. Do you think maybe this is why physicists try to fit everything into such a standard? Is it not just proper scientific methodology to try and make sure that everything fits into rules and patterns we have been over and over testing, or I think using over and over again? Wouldn't it be irresponsible to not consider that unbeautiful data could have something missing in it? So what about the flip of the coin? Going by this, wouldn't theories led by beauty actually be important?
So it's not so much that I'm generally against beauty. I'll have to put this ahead. It's that I'm saying we shouldn't start with very specific notions of beauty that physicists have come up with for some peculiar reason, and then they have formulated them in mathematical terms, and now they're getting stuck on them. Like, for example, this notion of technical naturalness or grand unifications. There may be other types of beauty which we just haven't discovered, and if we continue doing what we've been doing so far, we'll never discover them because we keep doing the wrong experiments. I mean, I agree insofar that science is all about covering patterns. That's basically the only thing we do. But do these patterns have to appeal to the sense of beauty that we are born with? I think there's no particular reason. For example, our perception that symmetry is beautiful in certain ways, that very plausibly has evolutionary origins, because organisms that are symmetric are more likely to be healthy. So this is something that we watch out for. And I'm not a biologist and I don't know a lot about this, but I think this is roughly the way that it works. But why should those notions of beauty that work for flowers also tell us something about the fundamental particles in the standard model? There's just no good reason for this. But of course, those fundamental theories, they may have other types of beauty that we just haven't thought about so far.
Amazing, amazing. And I can't wait until we see the impact of this kind of inclusive methodology of adapting all of the simple and beauty and complex physics all together when you are building a research aspect. So my question this time, because I think we addressed a lot of the audience question, and I had a question for you. You said that there has been limitations and challenges in the past because of the availability of data when it comes to building certain analysis. My question for you, would you think that an element of a crowdsourcing science is a viable solution to build more collaborative systems and ecosystem around resolving specific research aspects in physics? We've seen through the pandemic, researchers really capitalizing on this kind of crowdsourcing for scientific notions and scientific ideas to accelerate, for example, genomics analysis and simulation and whatnot. Do you see it happening in physics? Maybe to have accessibility to data, accessibility to multiple, I would say, diverse approaches of research. You talked about Maxwell, being the theorist and his colleague being the practical aspects of the experiment. So, can you see crowdsourcing science as a positive tool or a negative tool in improving the data accessibility?
So generally, I would say it's a positive tool. The question is always, do researchers think it's worth the time, right? So when it comes, for example, to the data accessibility, this is something which has been discussed, like, I don't know, since I've been in physics. And it's slowly getting better because a lot of publishers now require that you make your data available. At least in principle, they should require it. And for what large collaborations are concerned, that's the thing. It's usually possible for you to get your hands on the data. There may be a delay, like 2 years or something, where the collaboration has the chance to get all of it out of the data that they wanted to, and that makes sense. They have kind of a they had the work, so now they should have the right to do what they want to do first, and then other people can have their go. When it comes to smaller institutions, it also depends very strongly on the country. Then it may be very difficult to get your hands on the data. And there are various reasons. Maybe they're concerned about competition, or maybe they just don't know how to present the data. That's also a problem. I mean, usually the thing is you have a lot of raw data that is completely useless if you don't know exactly what the experiment looks like. So normally the data that you can share with other people has to be cleaned in some way so that other people can even work with it. And they may not have the resources to even do this. And so the easiest thing is to just not do it. So that's one thing. But also I'm very much on the theoretical side. And I think on the theoretical side, this is something that this sometimes keeps me up at night. I have this impression that all the knowledge that we need to solve those problems is out there somewhere. Someone has found it already. It's just that no one has been able to connect it. And and this is something where I think that artificial intelligence can actually help us make a lot of progress, because there must be connections in the published literature that you can find out just mechanically by figuring out who cites who in which connection and which are the links that haven't been made. And this is really something that I wish someone would look into. I know this has been done a little bit in other fields, like in chemistry, they've been looking for certain molecules that have certain properties, and they could predict this from the published literature and actually made correct predictions. Totally amazing. And I think in principle, this is something that should be doable in all fields, and it could unlock a lot of progress.
I think I'll take your note and your call to heart, because it's a very dear notion for us. I work for Women in AI as well, global community, and we do have researchers in the field searching for a great impact, especially in science, that they could work on a great impact project. And I think this is a great impact project. And this is why I suggested crowdsourcing, because then you develop an accessibility to an open data platform. You might not be interested in processing the data, but there might be other entities who would be interested in just cleaning the data, processing it, and providing it for scientists like yourself and others. So I am so happy. We're all so happy and inspired. I think we go home with a huge level of excitement and insight for what you have delivered tonight about the balance in between simplicity and beauty when it comes to physics. And I would call it balance because I could hear the inclusive call in your tone when you said, I'm not saying that we should do simplicity and discard beauty, or but try to strike a balance and not be omitting the possibilities and potentials that exist in the future. You talked about what keeps you up at night. And I want to ask you for your final, any final words that you want to tell us about what keeps you up at night and excitement of what would build a better field for physicists like yourself and for your team.
Well, I'm afraid the things that keep me up at night are most often more negative things. So I'm trying to think of something positive, forward-looking. So yeah, for example, I actually think I'm much more optimistic about progress in the foundations of physics than most of my colleagues, because most of them have this point of view that we're like really, really close to finding a theory of everything, and that'll be the end of the story. And I don't think that's going to happen. I think we're going to solve one of those problems, like one of the big problems, and that will just open up an entirely new area of research. And it will also bring a lot of technological progress that will allow us to develop new experiments. And I don't think we're anywhere near done with the foundations of physics.
It must be inspiring, not only for people in physics, but everyone who is working in industry and technology around our audience. Thank you so much for being with us tonight. It has been a pleasure. I'd like to also extend my thanks to the Institute for hosting you tonight. Dr. Sabine Hossenfelder, it has been an absolute pleasure. Thank you so much.
Thank you.